In this video, we'll practice a freefall problem. Freefall is a great example of one-dimensional motion that occurs in the vertical direction. Like all kinematic problems, the solution hinges on 5 key variables. They are the displacement, delta d, the initial velocity, vi, the final velocity, vf, the acceleration, a, and time, delta t. We'll be given some of these values and asked to solve for the rest using the kinematic formulas. What makes the freefall unique is the fact that the acceleration is always known to us. It's the constant acceleration due to gravity, which is 9.8 meter per second squared. And this value is always known to us, even when it's not explicitly stated in the problem. Now, before we get to the numbers of these variables, let's get organized by drawing a diagram and set up the coordinate system. So here we have a baseball. It is thrown up, it reaches to its peak, and then it heads back down to the ground. So this is the ground. Since the baseball's motion is only vertical, we don't need a full x-y coordinates. Okay? We can just use a simple y-axis to track its movement. Once our y-axis is in place, the most important decision we'll make is to choose a positive direction. And this is very important. It will affect the sign of every value we're going to use. Okay? For free fall problems, it's often convenient to define downward as the positive direction. Okay, so this is the positive direction. We'll solve the problem using this approach first, and then I will show you how to do it with upward as positive. You will see we'll get the same answer either way. Now that we've all set up, let's figure out the values of our variables. Besides the constant gravitational acceleration, we are told that the initial velocity is 20 meters per second. But we have to be very careful here. The baseball is thrown upwards, but we chose downward as the positive direction. This means our initial velocity must be a negative value. So our initial velocity should be negative 20 meters per second. Then we also know the time for the entire journey is 5 seconds. So delta t is 5 seconds. What we are solving for is the window above the ground, or in other words, the initial height of the baseball, which is the displacement from the initial position all the way to the ground, which is the final position. So this is delta D. Now let's bring our kinematic toolbox and pick the right tool for the job. Let's check these kinematic equations. And this third one looks good to us because it uses the initial velocity, delta t, the acceleration, and delta t again to solve for the displacement, delta d. Now let's copy it. Delta d equals to the initial velocity multiplied by the delta t plus 1 over 2, and the acceleration in our case is the gravitational acceleration, g, and then delta t squared. Some of you might be thinking, wait a second, won't this give us the total distance of the baseball traveled, like going up and then back down? And the answer is big no. This equation solves for the displacement. Remember, displacement only cares about the starting point and the ending point. It doesn't care about the path taken in between, right? So using this equation, we'll get the initial height of the baseball rather than the total length of its trip. For the rest, it's easy. Let's plug in the numbers. So delta d equals to the initial velocity vi is minus 20 meters per second. Then delta t is 5 seconds plus 1 over 2. G is 9.8 meters per second squared. Then times 5 seconds squared. So it equals to 22.5 meters. So the height of the baseball is 22.5 above the ground. Okay, now let's try this again, but this time we'll define upward as the positive direction. And this is going to change the signs of the variables. Since our initial velocity is pointing up, which is in the same direction as our positive y direction, So this time VI is positive 20 meter per second, but gravity always pulls down, so the acceleration becomes negative. So G is negative 9.8 meter per second squared. Okay, when we plug in these values into our equation, delta D is VI delta T plus 1 over 2 G delta T squared. It equals to VI is 20 meter per second, delta T is 5 seconds again, plus 1 over 2. G is negative 9.8 meter per second squared, multiplied by delta T, which is 5 seconds, then squared. It equals to negative 22.5 meter. Why we have a negative sign here? Remember that displacement also have the direction. It is defined as the final position minus the initial position. Since we define up as positive, then this final position, which is the ground, is a smaller number than this initial position, right? So df is actually smaller than di. So a smaller number minus a larger number, we're going to have a negative value. This negative value simply indicates that the baseball's final position is below the starting point, which is exactly what we expect, right? So the actual height of the baseball is actually the magnitude of delta D, which is still 22.5 meter. So both coordinate systems give us the same result. The answer is B. So no matter which way you choose, you always get the same correct answer as long as you pay careful attention to the signs. If you use the wrong sign, say if you use VI is positive 20 meter per second and G is 9.8 meter per second squared and delta T is 5 seconds, then if you plug in these numbers, you're going to have delta D is 20 multiplied by 5, then plus 1 over 2 multiplied by 9.8, then multiplied by 5 squared. So you're going to have 222.5 meter. Then you're going to choose D, which is a wrong answer. I hope this video has made the free fall problems feel a little less daunting. If you found it helpful, please give it a thumb up and subscribe to the channel.